I've entitled this next chapter, Introduction to Surfactants in Water. A course on colloidal phenomenon should include a discussion of surfactants. This is especially important when the focus is on applications. These versatile species are ubiquitous, found throughout industry and nature. For consumer products, they are used in the food and drinks we consume, soaps and detergents we use to clean, pharmaceuticals that help maintain our health, cosmetics and hair products that enhance our lives, and the fuels and lubricants that facilitate our transportation. It would be difficult to identify a commercial product or process that did not require the use of surfactant chemicals. It would also be difficult to describe colloidal systems such as sols, emulsions, and foams, the focus of much of the remainder of this course, without understanding the role played by surfactant species. Given the versatility of these chemicals and the technology that accompanies each application, there exists a broad variety of perspectives for addressing the topic of surfactants. The emphasis here is more on the fundamentals of how these products work and why they are used. However, the discussion will also include a description of many of the more commonly utilized families of products and their origins, which will help with understanding the role chemical structure plays in determining the behavior of surfactants. The term surfactant comes from the contraction of the phrase surface active agent, which amply identifies what these chemicals are designed to do, move to the surface. In practice, surfactants are used at low bulk concentrations, usually less than about 10 millimolar, and located at surfaces and interfaces at concentrations substantially higher. Once these species arrive, they orient to reduce the free energy. In fact, most textbooks define surfactants as chemicals that lower surface and interfacial tensions. Although many chemicals will affect this, in practice, the designation surfactant is typically reserved for those molecules that demonstrate great efficiency and effectiveness in this regard. From this description of surfactant species, it may be difficult to understand their utility. Surfactants, along with water-soluble polymers, are the chemical components that make the creation, stabilization, and control of colloidal systems possible. They are part of many consumer goods, but are often used at low levels and go unnoticed. They are also commonly utilized by industry to facilitate production and remediation operations. Their tendency to locate at and influence surface and interfacial regions at dilute concentrations has led to their use as wetting agents, detergents, dispersants, emulsifiers, and foaming agents. The tendency of surfactants to accumulate at surfaces and interfaces and reduce free energy or the tension is a direct result of their structural characteristics. Both monomeric and polymeric surfactants used in water tend to possess both water-loving or hydrophilic as well as water-hating or hydrophobic components. That is, they are amphiphilic, both loving and hating the water. This dual character is what provides for the observed behavior of surfactants in aqueous systems. Shown here is a simple description of a surfactant used in water systems. The structure consists of a long or large hydrophobic tail, or hydrophobe, which is commonly an aliphatic species such as an alkyl group. The surfactant structure is capped by a small hydrophilic head group, or hydrophil, which is commonly an acid or base functional group or composed of hydroxyl groups or ethylene oxide linkages. The hydrophobe and hydrophil are well segregated from each other, emphasizing the surfactant's amphiphilic structure. The hydrophobe is the chemical component of the surfactant that promotes its movement to surfaces and interfaces due to its unfavorable interactions with water, while the hydrophil could be said to temper this process, helping to solubilize the surfactant structure in water. The hydrophil also acts to help orient the surfactant at surfaces and interfaces. This orientation is often what provides the benefits of a surfactant in water systems, for example by lowering surface tension or stabilizing a dispersed phase. Although the simple description of a surfactant is useful, remember that there exists a broad variety of structures that can provide surface activity. Also, small modifications in the chemical structure of a surfactant can produce rather significant changes in its performance. Otherwise, the chemical industry would not offer such a wide variety of surfactant species. Let's begin by reviewing the different types of surfactants available. Given the variety of such species, it is useful to place surfactants in various categories or families. There are a number of ways that this can be done, for example based on application, origin, amphiphilic balance, chemical family, etc. For industrial applications, the most common approach is to identify surfactants by their head groups or hydrophils. The first question to be answered is whether the head group is charged when the surfactant is placed in water, which splits the surfactants into two categories: those that take on a charge when they're placed in water, or ionic surfactants, and those that do not take a charge when placed in water, or non-ionic surfactants. The ionic surfactants can further be divided based on the nature of the charge or charges, specifically whether the charge is negative or positive, which divides ionic species between anionic or negatively charged surfactants and cationic or positively charged surfactants. In addition, there are surfactants that possess both positive and negative charges. These types of surfactants are said to be amphoteric or zwitterionic. Based purely on the nature of the head group, 4 distinct categories of surfactants have been identified. As one might expect, the use of surfactants is not equally distributed amongst these 4 categories. To determine the relative use of these different types of surfactants, it is useful to examine market data. Here we review international sales data from 2012. As you can see from the sales distribution, the combination of anionic and nonionic surfactant account for most of the worldwide surfactant sales. Although anionic species have dominated the market for decades, the trend in recent years has been towards greater use of non-ionics due to the lack of biodegradation for many anionic species and an increasing emphasis on the environment. Cationics compose only a small portion of the surfactant sales, due primarily to cost and possibly potential toxicity, and even fewer amphoteric species are sold. This pie chart shows the general use categories for surfactants. Keep in mind that the market can be broken down in a number of different ways and parsed to greater and greater degrees. Here, industrial and institutional appears to encompass all use by institutions for maintenance, for example, for cleaning, and all industrial uses including food, synthesis, processing, cleaning, etc. Detergents include detergents used for household and industrial applications, for example, for clothes washing or dishwashing. Personal care includes shampoos, soaps, makeup, and other such products. Fabric softeners are used to give washed clothing and other fabric products a softer feel. Here is where we commonly see the use of the cationic surfactants. It should also be noted that in recent history, international or total sales of surfactants has increased every year, and this trend is expected to continue into the foreseeable future. The most used category of surfactants are anionics. These are surfactants that take on a negative charge when placed in an aqueous solution. This provides them with a high water solubility, but a low solubility in oils and fats. Anionics are relatively cheap to manufacture, and as a result are used in a majority of detergent formulations. Most possess linear alkyl hydrophobes containing 8 to 16 carbons. Anionic surfactants can be further categorized based on the nature of their hydrophils, with most being salts of sulfates, sulfonates, and carboxylates. Use of phosphates, which are not shown here, has been reduced significantly over the past decade due to environmental concerns, but they're still available for various applications. Most anionic surfactants are sold in the form of neutralized salts. Capital M superscript plus or M plus is used here to represent the positively charged metal counterion associated with the ionized acid functional group. Although we will not discuss it in detail here, the behavior of anionic surfactants can be strongly influenced by the selection of its cation. Use of sodium or potassium counterions results in a reduced interaction between the ionized acid functional groups and the counterion, providing greater ionization and increased surfactant water solubility. Use of cations such as ammonia, amine, amide, ethanolamine results in decreased ionization and a reduced surfactant water solubility. In other words, minor modifications such as our choice of a counterion can have a significant impact on surfactant behavior. The second most utilized surfactants are the nonionics. Rather than a charged head group, nonionics possess a large polar group. Without charge, which increases the solubility of organic species by orders of magnitude, a large group is necessary to provide the surfactant with the ability to dissolve in water. This group commonly contains a series of ethylene oxide or EO linkages. The advantage of using EO linkages is that it provides for greater control over behavior. Increasing the number of linkages increases the hydrophilicity of the surfactant. As will be discussed, the effect of this is more gradual compared with the impact of increasing the size of the hydrophobe on the hydrophobicity of the surfactant. Another interesting aspect of the EO linkages is their tendency to dehydrate with increasing temperature, which diminishes the hydrophilicity of the surfactant. Another less common approach to engineering greater water solubility in surfactant species is the use of glucoside linkages. As one might suspect from reviewing the structure of such linkages, each unit results in a greater increase in solubility when compared with EO units. Another difference compared with the EO linkages is that glucoside linkages are more stable with regard to temperature change. The third structure listed represents a family of copolymers containing both EO as well as polypropylene oxide or PO linkages, and molecular weights ranging from about 1,000 to 50,000 Daltons. These structures allow for a great number of variations in block arrangements as well as a range of block sizes. These changes provide for the engineering of a broad range of surfactant properties. The list of commercially available anionic and nonionic surfactants is quite long. Even if the discussion is narrowed to just surfactant families, it is still too extensive to review here. However, it is important to have some familiarity with the more commonly used surfactants. Fatty acid carboxylates, or SOAP, is a good place to start this discussion. SOAP is likely the earliest utilized surfactant and is still widely used today. Soaps are commonly generated from natural fats and oils, thus the starting materials for producing such surfactants are often renewable and biodegradable. Soaps are generated via saponification of triglycerides. Often, the triglycerides are partially or fully hydrogenated to provide for more stable products which are also more efficient. Saponification produces sodium salts of fatty acids. These chemicals demonstrate significant surfactancy in water, have a low oil and fat solubility, are low cost, readily biodegradable, and have a low toxicity. However, a major disadvantage of these surfactants is their limited water solubility and tendency to precipitate with multivalent salts such as calcium and magnesium to form whitish deposits in hard water. Significant resistance to hard water is obtained through the introduction of ethylene oxide linkages, which we will discuss shortly. The saponification process produces glycerol as a byproduct which can be isolated. Failure to remove the glycerol is thought to modestly reduce surfactant performance. This table provides the typical percentages of the fatty acid groups associated with triglycerides for a variety of different fats and oils. With use of natural sources such as triglycerides for starting materials, the soaps tend to contain a distribution of carbon numbers dependent on their origin. Some of these contain aliphatic hydrophobes that are unsaturated, which can be addressed through hydrogenation. Most commercial soaps are a mixture of fatty acid carboxylates produced from a variety of different fat and oil sources. This slide outlines another family of surfactants, fatty alcohols and Nonionic, which are obtained from natural fats and oils. Fatty alcohols can be petroleum-based, but are also commonly produced from coconut oil and/or tallow. The alkali-catalyzed reaction of these fats and oils with methanol forms fatty acid methyl esters, or FAMEs. These FAMEs are then converted to alcohols through reduction. For this surfactant structure, the hydrophobe is composed of a single alkyl group, which is typically 8 to 18 carbons in length. Because of their limited water solubility, fatty alcohols are typically not used for surfactant applications. Instead, the fatty alcohols are used to generate other types of surfactants. The synthesis of fatty alcohols also generates glycerol or glycerin as a byproduct. The glycerol can be collected and further refined. Here we review examples of how fatty alcohols are used to generate more useful surfactant structures. Alcohol ethoxylates, or AEs, are produced from the high-temperature reaction between fatty alcohols and ethylene oxide. The number of ethylene oxide linkages, or EO linkages, present is commonly indicated in the name abbreviation. For example, an alcohol ethoxylate containing 3 ethylene oxide linkages is abbreviated AE3. Alcohol ethoxylates possess a number of positive characteristics, including rapid biodegradation, low foaming tendencies, and a hard water tolerance. Although their primary use is in household detergents, alcohol ethoxylates are also used in household and industrial cleaning solutions, cosmetics, and for various uses by the paper, textiles, agricultural, and oil industries. A popular variation on alcohol ethoxylates are alcohol alkoxylates, in which the hydrophils are typically adducts of ethylene oxide and propylene oxide. Alcohol ethoxylates can be further converted into fatty acid ethoxylates. Ethoxylating soaps enhances their resistance to temperature, alkali, and hydrolysis even under strongly acidic and alkaline conditions, and it increases their water solubility and imparts a significant resistance to hard water. Significant quantities of fatty alcohols and alcohol ethoxylates are further converted to alcohol sulfates and alcohol ether sulfates using sulfur trioxide. The initial step produces a metastable pyrosulfate, which decomposes in the presence of more alcohol into alcohol sulfate and the alcohol ether sulfate. These acids are neutralized with a base such as sodium hydroxide, potassium hydroxide, or ammonium hydroxide, which provides for the introduction of different counterions. It is worth mentioning that the final products will tend to contain unreacted alcohol or alcohol ethoxylate, which can impact the performance of these surfactants either positively or negatively. Both of these types of surfactants are highly biodegradable and considered environmentally friendly, but the sulfate group makes them prone to hydrolysis under acid and alkaline conditions. The alkyl sulfates are quite commonly used in commercial products, especially lauryl sulfate, which is used in toothpaste, shampoos, and detergents. These types of surfactants also have good powder properties and are often used in solid detergents. Alcohol ether sulfates are typically obtained as pastes at 30 to 70% solids. The ethoxylation results in a distribution in the number of ethylene oxide linkages ranging from about 0 to 5. These linkages provide for better packing of head groups at the water-air interface, even with the charged sulfate group, which provides these surfactants with excellent foaming capabilities. They are used extensively in bubble bath, shampoos, and hand dish detergents. This table lists some common surfactant families used in industry. One of the problems with listing families of surfactants is nomenclature. There really isn't just one convention for naming surfactants. So a given surfactant family may have multiple ways of naming it. And I've tried to choose the most common way of naming that surfactant family. Also, if you look over on the right-hand side of that table, what I've listed there are some generic structures representing those family of surfactants, where R here usually represents an alkyl group, but it can be an alkyl group depending on the origin of the hydrophobe. And I've highlighted the first 6 because we've taken a brief look at each one of these families of surfactants. And what we focused on are these surfactants when they're obtained from renewable resources, fats and oils, but most of these surfactants can also be generated from petroleum sources. The main purpose for showing you this diagram is to emphasize the fact that the chemical industry has adapted to changing availability and cost of different starting materials, as well as societal pressures. Often, multiple routes are available to generate the same surfactant. So when there are petroleum shortages, chemical industry is able to shift over and look at different starting materials or raw materials for generating the same surfactant. As we begin our discussion on the performance of surfactants, it is useful to define a general parameter based on surfactant structure that provides insights on their behavior in aqueous systems. In particular, the ability of surfactants to quickly move to surfaces and interfaces in high numbers and stabilize these regions. These aspects are determined by the size and nature of both the hydrophobe and the hydrophil. In fact, it is actually the balance between the competing influence of these components that govern this behavior. For many decades, both industrial researchers and academics have worked to develop a parameter that measures this balance. However, it is the initial attempt to quantify this balance in a simple way introduced by a chemist working for a cosmetics company, which is most commonly used today. This is the Hlb scale. Hlb stands for hydrophilic lipophilic balance. This number is a gauge of the balance between a surfactant's water-loving and oil-loving or water-hating nature. Hlb numbers are one of the earliest and most successful attempts to develop structure-performance relationships for surfactants. This system was devised specifically to aid formulators in the selection of surfactants to form stable emulsions with oils. The idea behind it is to match the Hlb number of the surfactant or surfactant mixture to that of the oil to be emulsified. The Hlb number for the oil is the Hlb number of the surfactant or surfactant combination required to produce a stable emulsion with the oil. We'll discuss this further when we take up the topic of emulsions. The Hlb number for nonionics is simply a measure of how much of a surfactant's overall mass comes from the hydrophil, which is then placed on an arbitrary and dimensionless scale ranging from 0 to 20. On this scale, a set of isolated ethylene oxide or EO linkages, regardless of their length, would be a 20. That is, 100% of the mass is from the hydrophil. And an isolated alkane or alkyl group would be a 0. That is, 0% of the mass is from the hydrophil. A more meaningful example is a nonionic surfactant for which the hydrophil, a series of EO linkages for example, composes 80% of the molecule's mass. For this species, the assigned Hlb number would be 0.8 multiplied by 20, or 16. This approach was proposed by Griffin back in 1949 and is referred to as Griffiths Method. The equation shown explicitly demonstrates the simplicity of this approach, but for more complex structures, using this approach can be a little bit confusing. For example, deciding which components actually contribute to the hydrophil. It should also be noted that this approach cannot be used for nonionic surfactants that contain propylene oxide or butylene oxide units. Complicating things further is the fact that most surfactants are not a single highly purified mixture. Rather, surfactants consist of a distribution of species. Often, Griffiths' approach calculations can be based on experimental characterization of surfactant structures such as sulfonification numbers or acid numbers. And shortly, we will review an experimental approach for estimating the Hlb number for a given surfactant or for a mixture of surfactants. In principle, the Hlb system does not apply to ionic surfactants, but attempts are still made to apply the Hlb concept. For ionic surfactants, the hydrophil is often small, but is found to make an extraordinary contribution to the surfactant's hydrophilicity. This is why seemingly unrealistic Hlb values can be found in tables for ionic surfactants. The values fully account for the contribution made by an ionic surfactant to the overall Hlb number of a surfactant mixture. For example, if an ionic surfactant has an Hlb number of 40, it does not mean that 200% of its mass is from the hydrophil. This number reflects its true contribution to a mixture of surfactants in which Hlb numbers are assumed to be additive. That is, the overall Hlb number for a surfactant mixture is equal to the Hlb number for the individual surfactant components multiplied by their mass fractions in the surfactant mixture. The Davies Method for estimating a surfactant's Hlb number was devised in order to help estimate the Hlb numbers for ionic surfactants. This method assigns an Hlb value to each type of functional group, which we've indicated here with a capital H subscript I. Summing the Hlb values for every group in the surfactant molecule and adding 7 yields an estimate of the Hlb value for that surfactant. Shown here is a table with Hlb values for a number of molecular groups that compose a surfactant. You will notice that the hydrophobic groups have a negative number associated with them. This creates an equivalent but simpler formula and helps point out how Davies' method essentially starts every surfactant out with an Hlb value of 7 and then increases this value when we add hydrophilic groups and decreases this value when we add hydrophobic groups. It should be noted that ethylene oxide groups, or EO groups, and propylene oxide groups, or PO groups, have more accurate Hlb values listed under the miscellaneous section. So use these rather than simply summing up their individual components to get an estimate. Also, take care to only use the sorbitan ester and hydroxyl group Hlb values, 6.8 and 0.5 respectively, when considering those functional groups in the hydrophilic head head group of surfactants derived from sorbitan. Most notably, these are span and tween surfactants, which we will discuss later when we take up the topic of emulsions. This slide demonstrates the estimation of Hlb values of a surfactant species using the two approaches that we just reviewed. The example states that Igapol CO520 is a nonionic nonylphenolethoxylate. It's a nonionic surfactant commonly used in combination with anionic surfactants to stabilize emulsion polymerizations. Based on the provided structure, which is shown below, estimate its Hlb value using both the Griffiths and Davies approaches and compare your values with the experimental value of 10. As discussed, Griffiths' approach was developed specifically for nonionic surfactants and is better suited for such species. So let's start out by applying Griffiths' approach. Now, this is straightforward because the surfactant chemical structure is relatively simple. The first thing we have to do is calculate the contribution to the overall molar mass of the compound from the hydrophil. The hydrophil is on the right-hand side here, and it's everything after the phenyl ring. So it consists of 5 ethylene oxide linkages, and it's capped by a hydroxyl group. So its contribution is calculated as 5 multiplied by 44 grams per mole, which is the molar mass of a single ethylene oxide linkage, plus 17 grams per mole, which is the molar mass of the hydroxyl group. So I get a contribution of 237 grams per mole. Next, we take this value and we divide it by the total molar mass of the surfactant, which is given as 441 grams per mole. This gives us the mass fraction of the hydrophil in the surfactant. We multiply that by 20 to put it on a scale from 0 to 20. I get a value of 10.7, which is relatively close to the experimental value of 10. So let's move on now and repeat the calculation using the Davies approach. Although the Davies approach is considered a more general and fundamental approach based on molecular group contributions, it is found to work much better for ionic species. But let's go ahead and use it here for this non-ionic surfactant. So here's the Davies equation, 7 plus the summation of all the group contributions in the surfactant. And let's start adding them up. And the group contributions are given on the previous slide. So we'll start with the hydrophil here. We have 5 ethylene oxide linkages. So it's 5 multiplied by the contribution by a single ethylene oxide linkage, which is 0.33, plus the contribution from the hydroxyl group, 1.9. Now let's start adding up the contributions from the hydrophobe, starting out with the phenyl ring. Remember, this is going to lower the Hlb value. The phenyl ring has a contribution of negative 1.662. And now we're at the other end of the surfactant, which consists of an alkyl group, and the alkyl group contains 8 methylene linkages, and it's capped by a methyl group. So we have 8 methylene linkages multiplied by the contribution by a single methylene linkage, negative 0.475, minus the contribution from the methyl group, which is negative 0.457. We add all those up, and I get a value of 4.63, which isn't all that close to our experimental value, but we sort of expected this. There are correction methods that have been developed to allow use of a corrected Davies approach with non-ionics. One such approach is the effective chain length, or ECL concept. In qualitative terms, it is argued that the first few linkages of an ethylene oxide, or EO, chain make the greatest contribution to the hydrophilicity of the surfactant, but decreases as the chain is lengthened. Thus, shorter EO chains make a contribution that is considerably greater than that calculated using the group contribution parameters from the Davies approach. And here I'm showing an ECL value that I located in a journal article. It's from the Journal of Colloid and Interface Science from 2006, where they actually carried out the calculations to make this correction. And they get a value of 10.95, relatively close to the experimental value. So summing things up here, as expected, the Griffiths approach provides a better estimate for non-ionic surfactants. However, various correction approaches have been developed for using the group contribution method, which is considered more fundamental. Both the Griffith and Davies approaches appear to work reasonably well for estimating Hlb values for simple surfactant structures. For more complex structures or mixtures of surfactants, Hlb values can be gauged experimentally. The emulsion comparison test was introduced by Griffith for determining the Hlb values for oils and surfactants. As mentioned previously, oil is assigned the Hlb of the surfactant or surfactant system that is capable of producing a stable emulsion with that oil in water. For determining the Hlb of a surfactant, the test involves an oil and a surfactant of known Hlbs, and the surfactant for which we are trying to determine the Hlb value. A series of emulsions are produced with equal proportions of the oil and water in a fixed total surfactant content containing a range of known surfactant mass fractions. The emulsions are allowed to stand for a period of time, typically 24 hours, and their stabilities are assessed. The emulsion with the least amount of separation is used to estimate the Hlb of the surfactant being tested. As you might imagine, the results can be difficult to interpret, and often the tests must be modified to obtain meaningful results. The Hlb value for a given surfactant can also be estimated from empirical correlations. One successful correlation is between Hlb values and the cloud points for nonionic surfactants. The cloud point is the temperature at which a surfactant, for example in a 5% aqueous solution, becomes cloudy when heated. This data can be used to develop a curve that allows for the interpolation of Hlb values for other similar surfactants. Other parameters that can be used for such correlations include dielectric constants, heats of hydration, critical micelle concentrations, which we'll discuss later on, retention times for C18 reverse phase chromatography, and others. Although we have talked about wetting processes, I realize that we have not discussed the generation or behavior of colloidal systems yet. But I wanted to introduce this slide now, and then later on we'll come back to it again. Now, if we want to generate a colloid or promote a surface process, oftentimes this requires the use of a surfactant. The problem is that there are a lot of surfactants out there. And so how do we narrow the list down to the surfactants which are more likely going to work for a particular application? Well, we can do this based on Hlb number for the surfactant. For example, we find that more hydrophobic surfactants, those which have low Hlb numbers, are pretty good at preventing the formation of foams in water. And later on in this course, we'll discuss foams. If we're trying to generate an emulsion from oil and water, what we find is that if we use a more hydrophobic surfactant, one with a lower Hlb value, we're more likely going to get a water and oil emulsion. If we use a more hydrophilic surfactant, one with a higher Hlb number, we're more likely to get an oil and water emulsion. And later on in this course, we'll use Bancroft's rule when we discuss emulsions to explain this observation. Now, if we're looking at wetting a surface with water and we want to increase the spreading coefficient, we're probably going to have better luck if we use a more hydrophilic surfactant, one with a higher Hlb number. Now, these are just a few examples of how we can use Hlb number to narrow down the surfactants which are more likely to work for particular applications. This completes Lecture 1 of our chapter on Introduction to Surfactants in Water.